For centuries, the peak of mathematical prestige belonged to a single field. If you wanted to map the stars or predict the path of a falling object, you used the math of the continuous curve. Calculus was designed to measure change in real time. It allowed us to calculate the exact slope of a mountain or the accelerating velocity of a literal moving target. When Isaac Newton published his Principia in 1687, he provided a universal toolkit for a world defined by motion and physical rules. Even Albert Einstein relied on these principles of continuous curvature to explain how gravity bends the very fabric of space. But the defining problems of our time look different. Instead of tracking the smooth arc of a single planet, we are now trying to find patterns within billions of disconnected digital data points, from genomic sequences to global financial transactions. While calculus is excellent at optimizing a single path, it requires a massive structural framework to organize these oceans of discrete information. To process data at this scale, the math of curves needs a partner built for the grid. In a basement classroom at MIT, Professor Gilbert Strang began recording his lectures for the early internet. He spoke with a quiet enthusiasm that eventually drew in millions of students from around the world. The subject on his chalkboard was linear algebra, a field that for decades was often seen as a secondary prerequisite to the real work of calculus. Linear algebra is defined by its lack of curves. It is the study of flat planes, straight lines, and the rigid intersections between them. This inherent flatness provides the perfect organizational structure for the high-dimensional data that powers modern artificial intelligence. This diagram shows a matrix, the fundamental unit of linear algebra. A simple rectangle of numbers, with rows and columns categorizing vast amounts of information simultaneously. We can easily visualize how three variables look as coordinates in a three-dimensional room. However, human evolution didn't prepare us to visualize 4 dimensions, let alone 4,000. Our spatial imagination stops at 3. Linear algebra solves this by treating 10,000 dimensions exactly the same way it treats 2. The equations remain flat, predictable, and computationally efficient, regardless of the scale. It acts as the necessary bridge, allowing us to manipulate datasets that are too massive for the human mind to picture. The challenge is that these massive matrices are often full of noise. How does a computer identify the small percentage of data that actually contains a meaningful signal? Scientists use a method called singular value decomposition, or SVD. It is a way to distill a complex matrix into its most important foundational parts. First, the computer rotates the dataset to find a new perspective where patterns are easier to see. Next, it applies a stretch, elongating the primary trends so they stand out from the clutter. A final rotation aligns these components into a clean format. By rotating and stretching the data space, we can discard experimental errors and isolate the core information within any dataset. This framework is what makes deep learning possible. But there is a problem. While linear algebra organizes well, perfectly flat planes are too simple to represent the complex nonlinear patterns of human speech or visual recognition. To solve this, engineers introduce a mathematical fold. By using piecewise linear functions, a straight line breaks and bends into different slopes. Repeating this folding millions of times, these flat planes tessellate into a surface complex enough to approximate anything. This is how a neural network learns. It uses the structure of linear algebra to hold the data, and the optimization of calculus to fold the lines until they perfectly match the patterns we want to understand. We have transitioned from humans manually deriving the laws of nature to an era where we build systems to find those laws for us. From generative AI to the algorithms that manage our global logistics, the modern world is increasingly defined by how we process these hidden matrices. In a landscape of shifting data, mathematics provides a consistent sense of symmetry and structural logic. Our most widespread technologies ultimately rely on this quiet partnership, the precision of the curve and the immense flat geometry of 10,000 dimensions.